Okay, continuity. We've talked a little bit about continuity already. Basically, a function is continuous if so the intuitive idea is it's continuous if you can draw the graph of it without lifting your pen from the paper. So, for example, this function here is a hyperbola. It's discontinuous at x equal 2. There's a break in the graph at x equal 2. It's continuous from minus infinity up to 2, and it's continuous from 2 to infinity, but we have a little break in the graph at 2, so where it's discontinuous. More formally, we say a function f is continuous at a number a if the limit as x goes to a of f of x is equal to f of a. And a function is continuous on an interval if it's continuous at every point on the interval. So this is, in this example here, for example, we have a hole in the graph, and f of 2 is equal to 2, but there's a little break in the graph there where we have the open circle. So the limit as x goes to 2 of f of x it looks like it's about 4, just judging from the graph, and it's not equal to f of 2, the limit as x goes to 2. So so anyway, so this is the formal definition. A function is continuous from the right if the limit as x goes to a from the right of f of x is equal to f of a. A function is continuous from the left if the limit as x goes to a from the left of f of x is equal to f of a. I'll go. So I already have this on the screen here, but I'll just go over it again. This is an example of a function that is discontinuous at a, this is what's called a removable discontinuity, because if we redefine the function, redefine f of a to be equal to 4 instead of equal to 2, then this will becomes a continuous function. So this is what's called a removable discontinuity. Here we have the postal rates that these were the proposed rates in January of 2018. It was 50 cents for the first ounce for first class meal, and 21 cents for each additional ounce or fraction of an ounce. So this is a transformation of the greatest integer function. So this double square bracket means the greatest integer less than or equal to 1 minus x. So we have, these are what's called jump discontinuity. So just defining one point is not going to remove the continuity. So it's this is not a removable continuity, but it's a jump continuity. It says the function jumps up to 1 ounce. The rate is 50 cents, and then it jumps up. If it's a little bit more than an ounce, it jumps up to 71 cents. So that's called a jump discontinuity. Some of the properties of continuous functions, if f and g are continuous at a point A and c is a constant, then f plus g will be continuous, f minus g is continuous, the constant times f is continuous, f times g is continuous, f divided by g is continuous where it's defined. Which of the following are continuous at x equals 0? Actually, I should mention here, I forgot to mention that following functions are continuous on their domain. So polynomials, rational functions, root functions, trig functions, inverse trig functions, exponential functions and log functions. So these are continuous where they're defined. Some of them have some discontinuities, but they're continuous where they're defined. So exponential and cosine are both continuous, and if we add them, the sum of two continuous functions is continuous. The difference of two continuous functions is continuous. The product of two continuous functions is continuous. E to the pi is just a constant, so a constant times a continuous function is continuous. E to the x divided by cosine of x. So the question is whether it's continuous at 0. There are some places where where this ratio is undefined, but cosine of 0 is 1, so there's no problem with that being undefined here, if as long as we're evaluating it at 0. So it's going to be continuous at 0, and also cosine x divided by e to the x is continuous. Theorem: if g is continuous at a and f is continuous at g of a, then the composition f composed with g is continuous. So the question is which of these are continuous at 0, and so cosine is continuous at 0. Cosine of 0 is 1. Exponential is continuous at 1, so that's continuous. E to the x is continuous at 0, and the cosine is also continuous at 0. So cosine of 0 is it's be cosine at 1, rather. Cosine e to the 0. Cosine at 1 is continuous at that point. 1 over 0 is not defined. So these last two are not continuous at 0, because 1 over 0 is not defined. I skipped this example here. I meant to do this example earlier. This is an example of an infinite discontinuity. As we approach 2 from the left, f of x goes to plus infinity. As we approach 2 from the, as we approach 2 from the right, f of x goes to plus infinity. As we approach 2 from the left, f of x goes to minus infinity. So there's a gap in the graph there, and that's called an infinite discontinuity. Okay, so here's another theorem. If f is continuous, and this will be very useful to us. If f is continuous, then the limit as x goes to a. Oh, okay. If f is continuous at the limit as x goes to a of g of x, then we can take the limit inside inside the function. So it's the limit of f of g of x is equal to f of the limit of g of x. So we can use this to evaluate the limit as x goes to infinity of e to the 1 over x, and this is going to be limit as, okay, so we want to take the limit inside. So this is e to the limit as x goes to infinity of 1 over x, and this is this limit as x goes to infinity, 1 over x goes to 0, so this is e to the 0, which is 1. Okay, and then we have another theorem here. It's called the intermediate value theorem. If f is continuous on an interval a to b, closed interval, and f of a is not equal to f of b, and n is between f of a and f of b, then there's a point on the interval, on the open interval, such that f of c is equal to n. I think this theorem will be clearer if we give an example. So let's do an example here. So this example here, we want to solve x cubed plus x plus 1 equals 0. And so we wanted to check to see where there might be a solution. So if we plug in -2, A, we have -2 cubed plus -2 plus 1 is going to be -9. And -1 cubed plus -1 plus 1 is going to be -1. And then B, we have 0 cubed plus 0 plus 1 is equal to 1. And let's go on to C. We have 1 cubed plus 1 plus 1 is 3. D, we have 2 cubed plus 2 plus 1 is equal to 11. E is noted above. So anyway, we have a sign change from on this interval here between when x equals -1 and x equals 0. We have a sign change. So this is a clue that we'll have a 0 on that interval. So I'll make a little graph here. To sort of illustrate this. So we can regard this as a function. Let's say this is f of x. F of x is equal to x cubed plus x plus 1. F of x is equal to f of -1 is equal to -1. So this is right here. And f of 0 is equal to 1. That's right here. And this is a polynomial function, so it's continuous. So there's no way to get from this point to that point without going through 0. Okay, at some point in there has to be some value x between -1 and 0. F of x has to be 0. So there's a point in there somewhere. We don't necessarily know what that point is, but somewhere between -1 and 0, we have a f of x is equal to 0, and that's by the intermediate value theorem for continuous functions. Okay. And here's another example. We have sine of x minus a half times pi over 3 minus 2x. Let's see. So this is not going to be continuous at 3/2, but it's continuous at other places. So let's see what values we can have. If x is 3/2, that you have denominator 0. So let's say f of x is equal to this expression here. So we want to know in part A, f of minus 2. This is going to be sine of minus 2 minus a half is minus 5/2 pi over minus 2 times minus 2 is 4, it would be over 7. So minus 5 halves pi, we're going, it's going to be, we go around the circle once, right? You have so minus pi over 2 is going to be down here. So if we go around the unit circle in this direction here, oh, we want pi over 2. Okay. So pi over 2 is up there. If we go in this direction, we pass pi over 2. Let's see. Oh, we want minus pi over 2. Okay, so we're going. So the angle is negative. So we're going. We want to go in the clockwise direction. We have the positive angles, but if in the counterclockwise direction, we have the negative angles. So we're going counterclockwise in one complete circle and then another half. So we land at minus pi over 2, and the y-coordinate there is -1. The y-coordinate at that point is -1, so it's going to be -1 over 7. And then if we do a sine of, or f of -1, -1 plus a -1/2 is going to be -3/2. So sine of -3/2 pi. So then we're landing up here, and that's going to be positive, and that's over -1 times 2 is 2, 2 plus 3 is 5. So this will be 1/5. So we do have a sign change there between x equals -1 and x equals -2. There's a f of x has a sign change. So let's see if there's some additional sign changes here. If we do f of 0, 0 minus a half is minus a half. So this is sine of minus pi over 2. And the denominator will be 3 now. So this is going to be a -1/3. So we have another sign change there. And then C, the f of 1. 1 minus a half is a half. So now we're going in the positive direction. And see, 1, the denominator is 1. So this is just going to equal 1. So there's, we have a lot of sign changes. So D, we want to do 2. 2 minus a half is 3/2. So we have sine of 3/2. And over -1. And sine 3/2 is going to be a -1. Okay, so this is going to be a -1 over -1, which is 1. Okay, so okay, so we have a sign change on A between -2 and -1. There's a sign change. So part A, and there's also sign change between, this is -2 and -1, 0, 1 and 2. There's a sign change between x equals -1 and x equals 0, and there's a sign change between x equals 0 and x equals 1. So there's A, B, and C would be guaranteed to have a 0. We can't say that about D necessarily. There's no sign change for one thing, and also there's a discontinuity there when x is 3/2. Okay. Okay, so Okay, so this one here, we have a function, piecewise defined function, f of x equal x squared plus 1 if x is greater than or equal to 1. F of x is equal to 5 minus kx if x is less than 1. And we want to find the value of k that would make the function continuous. So that means these two formulas have to agree at 1. So f of 1, if we evaluate both of these at 1, in order for it to be continuous, they both have to be have the same value at 1. We 1 squared plus 1 if x is greater than or equal to 1. 5 minus k if x is less than 1. So 5 minus k has to be 1 squared plus 1, let's say, it has to equal 5 minus k. So we could add k to both sides of the equal sign. And 1 squared plus 1 is 2, so we have k plus 2 is equal to 5. Subtract 2, that means that k is equal to 3. So if k is equal to 3, then the function would be continuous. So that means that f of x, if it's to be continuous, x squared plus 1 if x is greater than or equal to 1, and 5 minus 3x if x is less than 1. And that way they both have the same value at 1 and the boundary between the two formulas. And that concludes this presentation.